that, I mean, so we'll do Hilbert-style, we'll do a Hilbert-style proof system in some more detail. There is an important theorem that we have to prove before we can do that, but we will also look at other things about formal theories. Yeah, right. So let's first go to the. So a formal theory basically consists of some language. It's a formal language, and a collection of axioms which are subsets of that language, which is a subset of the language. Or of course, if you have an infinite subset of axioms for the theory, then you might want to think of them as axiom schemas, which so that they are finitely expressible, and a set of inference rules. Yeah, so that's so this is what. So usually, as I said, this formal language is inductively defined, and therefore membership in the language for any string is decidable, and similarly the axioms should all be a decidable subset. They could be infinite, but this should be a decidable subset, and then the inference rules are essentially written in this form. Essentially we look at so inference rules can often be represent infinite relations in which this one thing is one statement is a direct consequence of some one or more other statements, and since it has to be a decidable relation, even if it is infinite, what we expect is that there will be some pattern matching and substitution way of expressing this infinite rule, this infinitary relation. Yeah. So you can think of these x. So in a rule of the form x1 to xm yields y, you can think of these x1 to xm and y as shapes or skeletal shapes of the formulae, which have to follow a certain structure, right, and the structure is defined by the syntax of the language, right. So, right. So, there are some basic theorems which might be called meta theorems about formal theories in general. One is and of course, remember that formal theories are pure syntax. So, the question of how useful or applicable or consistent those theories are really depends on connecting them up with the semantics, but that we will worry about that later. So, right now we will just look at what is known as proof theory. So, in general in a formal theory, we expect that the theory is monotonic on the assumptions, on the set of assumptions. So, if gamma is a subset of delta is a set of assumptions, then if whatever gamma can prove is also provable from delta, because I need to use only whatever assumptions are there in gamma and they are all there in delta, right. And so, this compactness, so this is this is not really a compactness theorem, but because of its connection with the compactness theorem that we have already proved, I am calling it compactness. But the main point about this property is that when we talk about a proof or provability, we are talking about provability in a finitary sense. So, you cannot, I mean, there are only the proof of any statement psi from a possibly infinite set of assumptions delta. If there exists a proof, it has to exist from a finite subset of that set of assumptions. So, even if delta is infinite, when we talk about a proof, we say that there should be a finite subset of assumptions from which the proof is obtained. Yeah. Okay, and then substitutivity, of course, is just that this is a standard method of splitting up a theory into lemmas and theorems, right. So, if I have a set of assumptions delta from which I can prove some statement psi, and each of those assumptions can be proved from a different set of assumptions gamma, then from gamma I can prove psi. That is so psi is provable from gamma essentially because each of the assumptions in gamma is also provable from this. Each of the assumptions in delta is also provable and therefore, I can split up my proofs into several such theorems or lemmas and so on and so forth, which is how formal theories are normally organized. Yeah. Which is how normal mathematical theories are also organized. We have lemmas, theorems, corollaries, they are all the same things, it is just that in terms of provability they all mean the same thing, and the name lemma or theorem or corollary just refers to certain value judgments firstly about the importance of the result. So, Koenig's lemma, probably Koenig did not think it was too important, so he called it a lemma, but the rest of the world seems to think it is very important, and Tukey's lemma similarly seems to be important enough to be called a theorem. But corollaries of course are some things that directly follow from theorems, but they are also theorems in that sense. So, there is only one notion of a formal theorem, though there are many different notions based on value judgments of whether something is a lemma or a fact. So, I have a hierarchy fact, which means it is completely trivial to prove. A lemma is something that is usually used to prove a theorem, and a corollary is something that directly follows from a theorem. So, that is those are the kinds of value judgments we make while organizing a theory, but in a formal sense all of them are the same notion. Yeah. Okay. And they actually allow us to organize formal theories and structure them in a certain way. Okay. So, we will do an example proof. We also looked at this Hilbert-style proof system, where we have these axiom schemas S, K and N and this rule of inference called modus ponens. Yeah. Right. So, here is a simple theorem. This is essentially the reflexivity of the conditional. Yeah. So, you have to prove phi r of phi from an empty set of assumptions. Okay. So, here this gamma is an empty set and you are going to prove phi r of phi. So, phi r of phi then is a theorem if you can find a proof for it. The normal way we write proofs in mathematics, and we should be writing it that way, is that every step is somehow justified. Yeah. So, well, so you will find that these Hilbert-style proof systems initially are not very easy to understand. Okay. So, here this justification is another of those peculiar things that I use, which are not normally used in most logic books. I directly use the notion of substitutions that we are all familiar with in pattern matching and programming and so on and so forth, and I use substitutions to as justification, so that it is easy to specify how we got this step, otherwise how did we get this step. So, this step essentially comes from the axiom schema K, and you are essentially looking for patterns to substitute for these variables x and y, right. Okay. Right. So, this step essentially says in the axiom schema K, if I replace x by phi and replace y by phi arrow phi, then I get this step. Okay. Right. So, you can think of these axiom schemas and rules of inference as essentially like Christmas tree templates. You know, you take Christmas trees, they have a lot of hooks on them in which the gifts are usually hung, but we can go further, we can hang other Christmas trees on them, for example, right. So, our formulas are of that kind. We can hang. So, these patterns provide that structural templates on which larger trees can be built up from smaller trees by hanging those trees on the hooks. Yeah. Okay. right. So, the next step, I mean, so this kind of proof is going to be completely non obvious and it is going to leave you quite befuddled, but we will go through with it and you will get used to it. The next step is this horribly complicated step which is actually justified by the axiom schema S. So, if you look at the axiom schema S, besides its normal connection with the S combinator in lambda calculus and combinatory logic, it also expresses basically the fact that the conditional distributes over other conditionals, right. So, this x arrow y arrow x is essentially implies x arrow y arrow x arrow z, right. So, the conditional distributes over the conditional. It's a very interesting and a powerful way of looking at the conditional, yeah. And this step is formed by replacing replacing phi for x, phi arrow phi for y and phi for z, right. So, you get this phi arrow 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 phi, yeah. So, okay, and then of course, then what I can do is I can notice that this step 1 and step 2 are essentially two instances of the hypothesis for the modus ponens rule. So, which means I can apply the modus ponens rule, right. So, the modus so here I have taken a shortcut. So, basically if you have two formulae having this skeletal structure, this pattern x arrow y and x, then I can essentially infer y. So, this is what the modus ponens rule does, and from this formula is essentially of the form x arrow y, where from here to here is x and from here to here is y, and this pattern as an abstract syntax tree is exactly the same as this pattern, and therefore, the modus ponens rule can be applied and you will get this pattern as the result, and that is what we have here, right. Okay. Of course, then but then from the k rule, by replacing phi for x and phi for y, I do get this phi arrow phi, and I can apply modus ponens on these two steps 3 and 4 to obtain phi arrow phi. So, essentially I have proved the so the reflexivity of the conditional has been proven by with no assumptions by simply resorting to the axiom schemas and the rules of inference. And this is how normally if you can think of mathematics as being presented, if it is presented formally. In fact, when I was in school and we were taught Euclidean geometry, we had to actually write it in this fashion. We had to write each step and give a justification for each step. Sometimes the justification would just be that it is an assumption, otherwise sometimes the justification would be that we are that it is some previous theorem or some previous definition or some such thing, but there had to be a number of steps, each numbered, and each of them had to be justified. I mean, that is so we did not write in free flowing English, we actually wrote in a 2-column format always, all the proofs in geometry. Yeah, okay. So, that trend seems to have gone off now, but that provides an important structure to the fact that each step does have a logical justification, right. But of course, as computer scientists, this is lousy. Actually, a proof is not such a sequence. A proof is actually a tree. In fact, it is what I would call an upside down tree, right. So, what we are going to do say is, so essentially this proof, what we refer to as a proof tree, there is a certain dependency. You apply a rule of inference on some previously obtained statements by doing a pattern matching. Okay. So, now this dependence can be expressed as essentially a directed edge, and if your proof was indeed non-circular, what you would get is a directed acyclic graph or a tree. If it is a directed acyclic, the only difference between a directed acyclic graph and a directed tree is that some nodes in a directed acyclic graph can have in degree more than 1. Okay. But then what you do is, if you replicate these nodes so that their in degree is 1, then you can actually get a tree. So, that is by replication you will actually, by appropriately replicating these such nodes. So, you will get a tree. So, what we will look at are, we will look at proofs as trees. Okay. So, essentially, so each node is a formula in this proof tree, and the leaves are either axioms, or in case there was a non-empty set of assumptions, they could be they could be drawn from the assumptions, or they could be for example instances of axiom schemas, right. Each internal node is an application of a rule of inference on some target nodes, right, by pattern matching and substitution. And the root node of this proof tree is the formula that was to be proved. Yeah. And of course, standard things for bookkeeping and so on and so forth is that you have to provide justifications sometimes. As you can see, even in a short proof like this, the justifications can be pretty complicated. If these justifications were not there, you would be quite puzzled to see all these phi's hanging around in strange ways, bracketed in strange ways, and you would not know how they were obtained. Yeah. So, you need justification. So that will be provided by these. So that is also something that will be provided by a label, let us say. So, our typical proof will look like this. So, the same proof. So these are the steps 1 and 2, okay, and this step 3, which yields this formula, is essentially the line segment extends right up to all the hypotheses of the rule that are applicable, and this below the line segment I get the conclusion. This is a separate leaf node which was actually obtained as an instance of the axiom schema K, and this line segment 5, which derives phi arrow 5, essentially spans these two steps from which the modus ponens rule was used, on which the modus ponens rule was used. Yeah. So, we will look at proofs essentially in this fashion. Yeah. Right. So a formal proof, as far as we are concerned, of a formula phi is a tree, is a proof tree rooted at the formula phi, such that the leaves are axioms or instances of axioms. Each non-leaf node is a direct consequence of one or more nodes at the succeeding level. I mean, the way we defined trees was that the leaf nodes have a level greater than the root node, right. I mean, so in this case we are turning the tree upside down, but still retaining the same notion of dependence, and the directed edge essentially talks about is the dependence of the conclusion from the hypothesis, right. And we would say that a formula phi is formally provable from gamma in the proof system this if there exists a formal proof of phi in the system H naught. If gamma is empty, then we say that phi is a formal theorem of the system. Yeah. So, this H naught is since we will be studying several different proof systems, this H naught is for the Hilbert-style proof system whose axioms we are K S n and MP, and we will study other proof systems also. Okay. Now, we come to an important. So, we will come to an important thing about. So, the notion of provability or formal provability is just that I mean okay, if phi is an axiom or instance of an axiom schema, then then phi is a formal theorem. If phi is provable or if psi is provable, then all leaf nodes in any proof tree of psi are either axioms or instances of axiom schemas. They could not be applications of rules unless there was some succeeding node preceding it. Yeah. Okay. And psi is an if psi is an axiom or an instance of an axiom schema, then it does not matter what assumptions you make, psi is still provable from those assumptions, except that you are not going to use any of those assumptions probably. Okay. And if I have an assumption, if I have a non-empty set gamma and I have an assumption phi inside gamma, I will claim that phi is formally provable from gamma. I mean this is, so this is just sort of from the assumptions gamma I can prove phi. I mean this is a sort of trivial statement. Yeah. Okay. So, next we come to this important theorem called the deduction theorem. Yeah. And this actually epitomizes most of the way we go about proving theorems in mathematics. So, the deduction theorem, so okay, there is some notation. Most logicians do not like all the set union and set brackets and so on and so forth. So, if you want to add to some assumptions, you just put a comma and add those assumptions, right. I mean, so this is a, so gamma comma phi proves psi is just means gamma union phi proves psi. Okay. So, the deduction theorem essentially says that if I have that if there is a conditional statement of the form phi arrow psi, that is provable from a set of assumptions gamma if and only if I, after adding phi to the assumptions, the new set gamma union phi can prove psi alone. This is exactly what happens if you see the most of the direct theorems that we prove in mathematics. You are given a set of hypotheses and then you have a conditional conclusion. So, your first step in any direct proof is to assume all the hypotheses and also assume the left side of the conditional, and your last statement usually is the right side of the conditional, and effectively you are using the deduction theorem to justify it. So, you are proving a different theorem. So, you had to prove this gamma proves phi arrow psi, but what you are actually proving is gamma comma phi proves psi, right, in any direct proof. Okay. Now, the proof of this is not easy, yeah, and so let us go about it in some detail. So, those of you who are doing other things besides logic, I think should wake up now. Okay. Right. So this is an if and only if theorem, it is a characterization theorem. So, which means that well, there are two parts to it. One thing to do is to, okay, let us go through these parts. I have tried to split it up into claims so that the proof is easier, but okay, let us see how it goes. So, what I am going to assume is that by putting in phi, including phi in the assumptions, I can prove psi. Given that assumption, I have to now so if I assume that psi is provable from gamma comma phi, that means there exists a proof tree possibly consisting of m different nodes rooted at psi. Okay. Let these m different nodes be psi 1 to psi m. Okay. Oh, by the way, there is no proof tree which is empty, right? I mean, it does not. If you are concluding something, then there is at least a root, which is also the leaf. Okay. So, now what we will prove is we will prove this much stronger claim. So, we are supposed to prove that gamma, from gamma you can prove phi arrow psi m, but we will prove gamma proves phi arrow psi I for all I. Okay. So, that is so if you can prove this claim, then essentially we have proved the implication in the theorem. Yeah. Okay. So, we will do this by induction. Okay. This induction, this is because of this upside down proof tree. Yeah. So, the upside down proof tree, and because of our definition of tree and levels of a tree, the root of the tree has a level 0. The leaves of the tree have levels much some positive integer greater than the root of the tree. So, which means that, but our inference actually starts from the leaves and goes down to the root. So, this induction is essentially because of that. So, the very first step I am assuming is going to be a leaf node. Okay. So, psi 1 is a leaf node. If so, then essentially each of these psi i's has some level which is essentially given by the level of psi 1 minus its level, right. Okay. So, I do this induction. So, this is my measure of induction, precisely because of the fact that I am using an upside down proof tree. If I had actually turned the tree upwards to the right way, then it would have been an induction on level of psi I. Okay. Okay. But okay. So, if this I am sorry, this should have been level of psi 1 minus level of psi I equals 0. So, that is the basis of the induction. Yeah. That means you are looking at a leaf node. So, think of it that the basis is that you are looking at a leaf node. If it is a leaf node, then clearly it is not obtained by application of any rule of inference. So, it is either an axiom or an assumption or an instance of an axiom schema. Okay. In the case of our Hilbert-style proof system, there are no axioms, there are only 3 axiom schemas. Okay. So, but of course, each instance of each of those axiom schemas is also an axiom. That is there are no separate axioms, right. So, then we have 3 cases to consider. One is that this psi I belongs to gamma, or it is the same as phi, or third that it is an axiom, right. So, we can separate out the case when psi I is phi from the other 2 cases. Okay. If psi I is phi, then this reflexivity theorem that we proved already shows phi arrow phi, right. I mean, it always holds. So, there is really nothing to be shown, right. So, the only interesting part of this case is when psi I is either an assumption or an axiom, or that is or an instance of an axiom schema. So, that means, so corresponding to each psi I, there is a subtree of the original proof tree, which I will call Ti. So, this Ti is rooted at psi I, right. Okay. Now, what I will do is, so this is how I am going to represent this Ti. Now, I am going to construct another proof tree Ti prime, okay, from using this proof tree Ti. Yeah. So, this whole thing is the proof tree Ti, and let us assume it is some step I or some such thing, or I prime if you like. And then what I do is I create a new leaf node essentially by appealing to the axiom schema K. So, this leaf node, so this one trivially follows from axiom schema K, right. Psi I arrow phi arrow psi I, it exactly matches the patterns given in defined in K, and so this must be true. But now from these two steps I can infer phi arrow psi I, right, by modus ponens, right. So, now let us assume the induction hypothesis that we have done this all for some up to some L, right, or for all measures below that level L, let us say, yeah, and that we have got to prove for some psi L, we have to prove that phi arrow psi L is provable from gamma, right. Okay. So, this psi L is a non-leaf node, it is neither, so therefore, it cannot be an axiom or a premise or an instance of an axiom schema. There is only one rule of inference in the Hilbert system, and so therefore, that psi L, that step psi L should have been obtained by an application of this rule. If it was obtained by an application of this rule modus ponens, then it must have, then the only way you could have concluded psi L is if there were some target steps I and j which enabled you to do a pattern matching and substitution according to the rule MP, right. Okay. So, there are some psi I and psi j such that they actually, without loss of generality, I am just assuming that psi j is of the form psi I arrow psi L, otherwise you could not have concluded psi L using modus ponens, right. So, you concluded from these two nodes I and j, if you concluded psi L, then one of the nodes, let us say psi I was just some formula psi I, and the other node psi j was of the form psi I arrow psi L, only then you could have applied this rule of inference and concluded psi L, right. Okay. So, now, but what we have to prove is gamma prove, and this is in the tree gamma comma phi proves psi L, right. So, we are looking at we started with the assumption that gamma comma phi proves psi, and we have gamma comma phi proves psi I, all of each, for each I they are subtrees of this tree, right. Okay. So, this is what we are going to assume. So, we are going to assume that psi j is of the form psi I arrow psi L in that proof tree, and since I and j belong to some target levels less than this level or higher than this level L. So, therefore, by induction hypothesis there do exist proof trees T I prime and T j prime, which prove from gamma, which prove phi arrow psi I and phi arrow psi j respectively. These are separate proof trees, right, because these are different proofs with the different sets of assumptions. So, now what this means is now each of these proof trees T I prime and T j prime, let us assume they have I prime nodes and j prime nodes respectively. So, T I prime is rooted at I prime, rooted at phi arrow psi I, and T j prime is rooted at phi arrow psi j, but psi j of course is psi arrow psi L. So, T j prime is rooted at phi arrow psi L, right. Now, what I am going to do is I am going to form a new proof tree T prime L from the from the two proof trees T prime I and T prime j. So, this represents T prime j. So, if I am going to now I assuming that our step numbers have to be different in each case. So, I am assuming that this proof tree T I prime has I prime nodes and this proof tree has j prime nodes, and if I am going to combine them I have to make step numbers unique and so on and so forth. That is that basic bookkeeping which has to be done. So, let us assume that this tree T j prime is rooted at phi arrow psi I psi l, right, and there is this tree T I prime rooted at phi arrow psi I. Okay. Now, I am going to take my j prime plus 1th step to be a leaf node which is an instance of the axiom schema S. So, look at this j prime plus 1, it is an instance of the axiom schema S, because phi arrow psi I arrow psi l can arrow, this arrow distributes over this arrow. So, you get phi arrow psi I arrow phi arrow psi l. Okay. These two steps j prime and j prime plus 1 are instances of the hypothesis of modus ponens, and so I can get the step j prime plus 2 by an application of modus ponens, which will essentially give me phi arrow psi I arrow phi arrow psi l. The tree T I prime is already rooted at phi arrow psi I. So, the steps 1 to I prime I rename them, I renumber them as j prime plus I prime plus 2 to j prime plus 3 to j prime plus I prime plus 2, and I have this root here, and these two steps essentially are instances of the modus ponens rule can be applied on these two to yield phi arrow psi l, right. Is there anybody who followed it? Yeah, is fine. Okay. So, this proof tree is my proof tree T prime L, and that proves that from gamma it proves phi arrow psi l, and that so the induction step is over, and therefore, the first part of the theorem is over. Yeah. So, the second part is the converse, and that is much simpler actually. So, here of course, we assume that we have proofs of phi arrow psi, we have a proof of phi arrow psi. Yeah. So, let T be this formal tree, may be consisting of m nodes for some m greater than 0. Then by monotonicity, so there are these, we had these 3 properties which essentially said if you keep adding extra assumptions, the previously proven conclusions still continue to hold. Okay. There is a question of supposing my extra assumption was the negation of some previous conclusion, does that previous conclusion still hold? And that is a valid and legitimate question, but the answer to that is yes, it holds, right. It still continues to hold. Okay. So, I mean, so we will define provable inconsistency in terms of that. So, in fact, what we will do is we will define that a set of assumptions is inconsistent if and only if every formula in the language can be proven from that. That is so in that sense it is still consistent with monotonicity, right. Okay. So, by this monotonicity theorem I can add this extra assumption phi and I still have my conclusion phi arrow psi. So, the proof tree does not change, So, the original proof tree for gamma proves phi arrow psi continues to hold also for gamma comma phi proves phi arrow psi. But what we can do is we can add this. So, this proof tree has m nodes, you added an extra assumption, you can also add an extra leaf node. So, I take this original proof tree T rooted at phi arrow psi, add this extra assumption phi, and I get a conclusion psi by a simple application of modus ponens, right. So, this is actually a very powerful theorem. In fact, without in any Hilbert-style proof system, without first proving this theorem, it is almost impossible to proceed further, okay. Because what it does is it greatly simplifies the proofs of several other kinds of theorems. So, the almost but notice that I had to use reflexivity somewhere, I had to use reflexivity somewhere. So, this proof was absolutely essential, okay, and it had to be done without the use of the deduction theorem. Okay. If you look at the deduction theorem, it is essentially about conditionals, whereas reflexivity is also about conditional. And from the deduction theorem, it actually, if I did not require to use reflexivity in the deduction theorem and I had the deduction theorem standalone, then I could have proved reflexivity trivially by saying phi proves phi, I mean that is it, right. But unfortunately, I did require reflexivity, and therefore, it is necessary to do that proof before actually proving the deduction theorem. But once you have the deduction theorem, lots of things become much easier. So, one of the did I what? Yeah. So, let us take, so reflexivity is one aspect. Let us look at something else. So, one other possibility is transitivity. So, you can look at this. So, essentially phi arrow psi comma psi arrow chi proves phi arrow chi. Okay. So, this is essentially transitivity of the conditional, yeah. And if it had been written as a theorem, as a formal theorem, then what one would have done is one would not have bothered to write these commas. Instead, actually one would have written it like this, right. So, if I had to write it as a theorem, as a formal theorem, this is how I would have written it. Is it clear, or should it? So, okay, as a formal theorem, what I would have written is this: phi arrow psi arrow chi arrow phi arrow. Oh, is this bracket right? No. Okay, I am sorry, this is not right. So, if I were to write it as a formal theorem, I would have written it as phi arrow psi arrow phi arrow psi arrow chi arrow phi arrow chi. This would have been the formal theorem, right. So, supposing you had to prove this theorem, now it is actually very simple. This whole theorem can be proven provided I prove. So, this is a formal theorem by the deduction theorem if and only if from the assumption phi arrow psi I can prove psi arrow chi arrow phi arrow chi, and this holds if and only if phi arrow psi comma psi arrow chi proves phi arrow chi. Okay. So, in fact, so it suffices to prove this by the deduction theorem, right. Now, how will I prove this? Right, that is what we are going to use. Yeah. Okay, so can somebody tell me how to proceed with this? Yeah. Okay, so we are going to you're going to assume phi. So if and only if phi arrow psi psi arrow chi comma phi chi, right. That is all. Okay. So, so if you prove this, it is actually sufficient, right. And how do we go about proving this? We start with this assumptions, and essentially from, so you have this, you have one leaf node. This requires some complicated manipulation, which, okay. I have this as a leaf node, I have this as another leaf node from which I can infer psi, and then I have this as a leaf node, and I already have this from which I can infer chi, and that is a 3-step proof, right. Okay. So, this the deduction theorem will considerably simplify a large number of proofs, right. There is also a connection that this deduction theorem gives you to let's take this, let's take all this together. Okay. So, what we are saying now is that we have what are known as direct conditional proofs, okay, in which certain assumptions can be made. Yeah. So, what we are essentially going to do is, we are going to look at this deduction theorem. So, we are going to assume, so this much, assume you got this. These are all, you can think of these as assumptions. Okay. So so these are assumptions from gamma, right. Okay. So, our gamma consisted of, hey, there was something else, was there something else? Psi arrow chi also, psi arrow chi phi, okay. Now, these are the assumptions we used. Okay. So, from these assumptions you prove chi, and essentially what you are going to do is, so you have a proof like this from these assumptions, and then essentially the deduction theorem allows you to discharge these assumptions. Okay. So, if you look at this purple stuff here, the deduction, you can actually go backwards on this step. So, I can actually think of this as so what I can do is I can actually from here I can actually discharge the assumption. So, I am using a different color to show that I am discharging an assumption, and this discharge of this assumption phi essentially means that I have phi arrow chi here, and then I can go one step further and discharge this assumption and get psi arrow chi arrow phi arrow chi. Okay. Then I can go another step further and discharge this assumption to give me essentially phi arrow psi arrow psi arrow chi arrow phi arrow chi. Okay. So, what this, the connection with programming languages and programs in general is merely this, that in order to prove this, I am initially making some assumptions. Those assumptions are create new scope for those assumptions, right. So, I will tell you what, I am looking for a suitable way of representing it in terms of trees, but so essentially what I am saying here is, so this is an innermost scope, okay, which has these assumptions 3, 2 and 1. Okay. Having discharged this assumption phi, I get an outer scope which has these two assumptions 2 and 1, which has, I am sorry, which in which this assumption it has these two assumptions 2 and 1, and then when I discharge this psi arrow chi, I get another scope which has essentially the assumption in which this is gone and there is only the assumption 1, and the outermost scope for which I have run out of colors is essentially this outermost scope which has no assumptions. Right. This connection with scope is not, I mean is not just incidental or trivial. there is the scope of the assumption. So, if you look at this tree, you are looking at increasing increasing nesting of scope levels, exactly like we see in a program. Okay. Further, these scope levels, now actually what will happen is the next important theorem will prove is a proof by contradiction, and there what assumptions are taken in order to get a contradiction become important, and so therefore, the scope of those assumptions becomes important. Yeah. So, we will see that next time. Okay. So, we will see that next time, and you will see the importance of scope.